And the next speaker is Pierre Le Doussal from CNRS and Ecole Normale Superieure de Paris. He will talk about large deviations for the KPZ equation.
Okay, thank you. So as you've seen in the previous talk, which was a collection of very beautiful results, there are a lot of things known now about typical fluctuations for KPZ. But the question for the KPZ equation, the question of the large deviation is much less known. And I'm going to talk here about a large deviation for the KPZ equation in two limits, large time and small time. And I will use results of integrability of the equation, meaning that I will need exact solutions which are available for some specific initial conditions, but they are exact results for arbitrary time. So in the previous talk you have seen the large time fixed point. To understand the large deviation, it seems like one needs to have some information about finite time, and that's what I'm going to use. So this work was done in collaboration, most of the work was done with Alexandre Tragenbrick, who is my student, and who is now actually looking for a postdoc, and I feel I should advertise for him. Okay, he's a quite excellent student. And so Jeremy already wrote the KPZ equation. I'm not going to put any epsilon. I'm going to put a square root of 2, however, because I want to have some specific factors multiplying the noise. And I'm going to, so it's a physics talk. Nothing will be rigorous except when I quote mathematicians. And I will, of course, think of the solution of KPZ equation actually has a collapse solution. So I will define the exponential of the KPZ field, or I will define KPZ field through the logarithm of Z, where Z satisfies the stochastic heat equation. So the stochastic heat equation with the multiplicative noise and with the Ito prescription. Okay, so before I talk about large deviation, let me talk about typical fluctuations. And just to summarize a little bit what was said in the previous talk, there are various initial conditions. So you have, here I will discuss the flat, the droplet, or as Jeremy called it, the narrow wedge initial conditions, also called droplet because the growth will be circular around this wedge. So the flat initial condition, of course, h is 0 at time 0. The droplet is this narrow wedge initial condition. And the other interesting initial condition is a stationary or Brownian initial condition where H0 is a Brownian, let's say two-sided Brownian. In each case one has, so I'm going to be interested in the 1 point height, the height at 1 point, sorry, at h of 0 and t. As you've heard in the previous talk, it goes linearly with time, plus some fluctuation t to the 1/3 times some random variable chi. And depending on the initial condition, this chi has three different distribution, either GOE Tracy-Widom distribution, or GOE Tracy-Widom distribution, or the Bike-Rains distribution in the limit of very large time. So this is usually called chi2. This one is actually chi1, which means GOE multiplied by some factor, which is 2 to the minus 2/3, which was also in a talk of Jeremy. And then the Bike-Rains distribution. Okay, so these three cases actually correspond to the cases where one can actually get an exact solution for the one-point probability distribution at arbitrary time. So these are the ones I'm going to discuss. So these are, of course, typical results about typical fluctuations. But now I'm going to ask about the tails of P of H and T. And H here will be, let's say, H0T minus this linear piece. Okay, so before I go to the large time, let me just briefly mention some things about short time. So for short time, as you know, KPZ equation becomes quite similar to Edward-Wilkinson equation, so the same equation without the nonlinear term. And in that case, at least at the typical level, this is true at the typical level, typical fluctuations. So in that case, H fluctuation scale like t to the power 1/4, just from the linear, solving the linear equation. But there is a large deviation form, which I will discuss in detail later, but let me indicate it now, which will have this form. So it will be a function of H divided by square root t, and this will be valid. So this is typical, but this is large deviation, so it's valid in a region where H is over the 1, so much larger than t to the 1/4. Now this function phi of H, we can obtain it from exact solution, and it has also been studied. So this is a list of papers on the subject. I will actually go through one by one later, but to show you the recent activity in the topic. And this function phi of H, one can obtain its asymptotics by also by what's called weak noise theory, and I'll come back to it, although I will not describe the method, which was developed by Korshunov. It's also called optimal fluctuation theory, and also more recently by Merson and collaborators, who wrote like 5 papers on this for various initial conditions. And the two set of results, which we get by exact solution and by weak noise theory for small time, actually agree. So let me go back to large time. And first of all, of course, one has to, well, the first thing is to look again at the typical fluctuation and what are the tails of these typical fluctuations. So these are questions about the tails of Tracy-Widom distribution in the typical regime. And let me recall some things about the tails of Tracy-Widom. Well, so then I'm looking at H over the t to the 1/3, but H over t to 1/3 being large over the 1, but large positive, for instance. So that would be the right tail. That's what I call the right tail. And it is known that it's a stretch exponential, and that P of ht is exponential of -4/3 h over t 1/3 to the power 3/2. So it has a 3/2 exponent, and the coefficient here is the same for flat and for droplet initial condition, and it's 2/3 for Brownian initial condition, just by looking at the bike-range GOE and GOE Tracy-Widom distribution. The left tail, so the left tail is the region where -h over t 1/3 is over the 1, but large, it's on the negative side. And as you probably know, the Tracy-Widom distribution on that side, so this is very easy to obtain from the Fredholm determinant formula of the Tracy-Widom distribution. This side is much more difficult and requires to solve the Palmve equation. And what you get is a cubic tail. So it's again a function of h to the t to the 1/3, but then there's a cube exponent. And this cubic tail is the same actually for the bike-range case, for the Brownian initial condition, and For the flat initial condition, it has a 1.6 instead of 1.12. So the question now is, what about large time, large deviation? Does the cubic tail extend to all times, or all value of h, sorry, or not? Okay, so this is what we addressed in this first paper on the top of the list with Majumdar and Sher. And so what we discussed in this paper is the large deviation. So we found that there was a large deviation regime. So again, this is typical. And the large deviation regime was when h was of order t. So it's basically when the interface is going a little bit slightly larger velocity than typical. So what we found is that on the right side, so meaning h positive over the t, h over t fixed positive, then p of ht takes a large deviation form, exponential minus t times some function which I call phi plus of h over t. So here there is a factor t, and this function phi plus, when its argument z is close to 0, should be 4/3 of z to the 3/2, because it has to match this behavior. And you can see that it does match, since you can write 4/3 t h to t 3/2. You can also write it as exponential 4/3 h t 1/3 3/2. And actually, I want to make this remark now, is that you can also write it as exponential of minus 4/3 h 3/2 over square root t. And this last form, so this is of course just the same thing, but this last form is exactly the same form as here. So it turns out that this right tail actually will also show up at small time, although here we're doing large time. Okay, now what about the left tail? On the left side, so h over t now is negative. So you have a similar large deviation form, but now instead of being exponential t, it's exponential t square on this side with a function phi minus of h over t. And again, this function phi minus should be cubic for small negative argument, to match, again, the cubic tail of Tracy-Widom. Okay, so how do we get to this? Well, first of all, there is some analogy with random matrix. Clearly, in the typical fluctuation, there is some random matrix coming out, because these are a distribution of largest eigenvalue of random matrix. But in random matrix theory, when you look at the largest eigenvalue, you can also look at the large deviations. And in random matrix, you also have a left tail, which is for the large deviation of the largest eigenvalue, which involves, for instance, for the GUI, some scaling function near the edge with the n square on the left side and with the n on the right side. Okay, so this is an analogy, but the other thing we did, well, first of all, I must emphasize that these functions, these large deviation functions, are not universal. So these are the large deviation functions for the KPZ equation. If you look at a model which at large time converge to the same KPZ fixed point, for instance, we looked at a polymer model, directed polymer model on a square lattice, which was studied by, solved actually by Johansson in 2000 with exponential weights, and which has some connection with complex Wishart matrices. Then one can actually, using Johansson result, one can actually calculate these functions. They have the same limiting behavior here, but they are different from the KPZ1. However, the behavior t and t square here are actually, the t and t square are universal. Now, how can we understand the t and the t square on the right side and on the left side? Well, if you suppose, let me again look at this directed polymer model. So this is a model where you have a square lattice, and let me call it x and t, and I'm going to write the lattice like this. So you have a square lattice with some weights, and you look at path going from here to here. So this is a discrete version, if you want, of the KPZ equation, or more precisely, if you take, so the model I'm going to describe is at 0 temperature, but if you were looking, and I will show you later numerical simulation, where you look at this model at finite temperature and you take the high temperature limit, you can scale it to KPZ equation. You scale it, so Z becomes the partition function of the polymer in a continuum in that limit, and it becomes via Kolop, the KPZ equation. But here I'm talking about a 0 temperature model, so it's a minimization of energy on a square lattice with random weights which are exponential on each site, and you're looking for the optimal path which collects these weights. And then there is for this model you can write, if I call H this optimal energy, going from xt to 0, 0, it satisfies some recursion equation like this. Plus some random variable which has exponential distribution. And you can ask now, how can I make the height at a given site smaller than the typical? Well, to do that, clearly, because of this recursion, I need to make the height at t-1 also smaller than typical, and so on. So eventually, I will have to make the height, the disorder here, smaller than typical in a region which is something like this, and which is the area which the polymer can go. So it's a wedge, and the area of this wedge is t square. So that's why one expects naturally to have t square on this side, and it's a collective effect. It's an effect which is a whole volume. On the other hand, if you want to have a larger than average, larger than typical, all you need to do is to have exceptionally good sites on some line. So it's just something, you need to have some good higher than average psi here on a line going from 0 to xt. Okay, so then in that case you expect exponentially. The probability of this happening is exponential of t. This is exponential of minus t squared. This is exponential minus t. Okay, so this is the argument. But now what about actual prediction for these functions? So the prediction that we made in this paper is that this function phi plus of z is actually equal to 4/3 of z3½ for all z, and this is coming from study of the moments of the partition sum, for which there are exact formula, and we know that they grow like exponential n cubed t, and from this one can actually deduce this, or at least have some constraint on this large deviation function. So this prediction we believe is correct, and until now has not been, well, actually I think it's more or less proved by Corwin and Gossal paper, although there's still some question about the prefactor, in the mathematical proof. But so this is presumably a correct result. So the other result that we obtain, which I'm going to argue now is wrong, but I'm still going to quote it, is this for negative z, so on the left side. And this was coming from analyzing a variant of Painlevé equation. So Jeremy and Ivan and Amir found that the finite time exact solution for KPZ can be expressed using quite complicated non-local Painlevé equation, so integral nonlinear equation. And by trying to put some ansatz in this equation, we arrived at this result. Well, it turns out this was not correct, or ansatz was not correct, and the correct calculation was made later by Sasarov, Merson, and Prolak in this paper, where they made a very clever guess about using some analogy with semi-classical limit in a quantum mechanical self-consistent problem for this solution, and arrived to some exact formula for phi minus of z, which I will show you later. I will derive it by some other method later. Okay, so is there a question at this stage? I'm going now to go to actual calculation of this phi minus. Okay, so this is not correct, and I will show how later. Okay, so yeah, so let me erase this and let me start again here. We're going to calculate this phi minus. The phi plus is quite simple actually, so phi minus has interesting structure. So we start from the exact solution of KPZ equation for the droplet initial condition, which we found with Pascual Calabrese, and there was also at the same time solution by Dotsenko, by Spohn and Sasamoto, and by Amir, Corwin, and Castel. But I will write it in a form which was written by Borodin and Gorin, which is very convenient for this analysis. So h again is the height at one point of KPZ. And here the expectation is over KPZ noise. And you can rewrite this as a Fredholm determinant. This was the solution, but there is a more convenient way to write it as an expectation, an equivalent way, over the Airy point process of something which looks like a Fermi factor. Okay, so this is the formula. So let me call this side 0 and this side 1. So there's actually a connection to fermions, which I'm not going to discuss, but which is also interesting. So the I from the Airy point process, meaning it's a point process whose correlation functions are all determinants. So it's a determinantal point process based on the Airy kernel. So I'm not going to rewrite the Airy kernel because Jeremy has been kind enough to write it for me. So you have this set of points. And now what is these points again? They are actually the limit of the edge of GUE on the matrix. So if you look at either the lower edge or the upper edge of GUE, eigenvalue of GUE on the matrix, with let's say a support between -2 and 2 in a large n limit, this actually this AIs is this determinantal Airy point process, and they are basically point which will, let's look at here, they will accumulate to the left. So you have 0, you have some here, and then they will start accumulating, and they will have some density, which in that limit here will look like the semicircle. Okay, so the density of this Airy point process is actually, so this is a mean density, is given by some Airy function. I'm not going to write it, but for large negative A, so this is A, this would be the density, it becomes essentially square root. So it's just semicircle when A goes to -infinity. And this will turn out to be very important for getting the tails of the KPZ equations. So we have basically turned the problem of tails of KPZ equation into a problem of studying the airy point process. So let me first make some remark on this formula. First of all, in a limit t going to plus infinity, clearly this is 0 unless all the AIs are smaller than minus s. So when t goes to infinity, this becomes a probability that all the eigenvalues of the GW are smaller than something, and this is by definition F2 of S, which is the Tracy-Widom distribution for the GW. On the right-hand side, and on the left-hand side, when t goes to infinity, essentially this is either 0 or 1. So this is 1, and the left-hand side goes to the probability that h over t1/3 is smaller than s. Okay, so you recover the correct limit, but this is solution valid for arbitrary time. Okay, so now let me write this. Let me explain now the method of cumulants, which will tell you, it will give you information about the left tail. So again, I have written this has exponential over the airy process. Well, I would say this thing of exponential of minus sum over I of some function phi of AI. So this is what's called a linear statistic problem in random matrix theory. So it's asking about probability distribution of sum of functions of eigenvalues, or eventually large deviation. In our case, we'll be interested in that regime. So what can I do to calculate something like this? Well, I can first of all do a bound. So I can, let me call this 1 again. So I can write that this 1, of course, has to be bigger than the exponential of the average. So I'm putting the expectation inside. And if I'm putting the expectation inside, I can just say that I can just use the density of the process. So I can rewrite it as exponential. Yeah, so what about this function phi ts of a? So this function phi ts of a is the logarithm of this Fermi factor. So it's log of 1 plus exponential t1/3 a plus s. And for large t, it will become essentially the same as t1/3 a plus s plus, which means the max of a plus s and 0. Okay, so this log of the Fermi factor becomes simply the max of a plus s and 0. And I'm going to insert it immediately there because this is the limit I'm interested in. So I'm going to rewrite it as t1/3 and then I put the density of the process. So this step is exact, apart from this large time limit. And now I'm interested now not in h over t1/3 over the s, but I'm interested in h over t over the something fixed. So I'm going to choose s to be minus the t2/3, so that the left-hand side 0 will go to the probability that h over t is smaller than z. And this variable z will be negative. I'm looking at the left tail. Okay, and so I'm going to plug this in there, but you see that I have to rescale A. So I'm going to rescale this airy process, and I'm going to write A is B times t to the 2/3, meaning that I'm looking at the airy process very far from here, so towards the bulk here, since t is large. Okay, so now it's a simple rescaling of this integral, and you can see that I can rewrite it like this. And then I have something which appears, which is that the density, okay, so this is just rescaling, but now this goes to a limit, which is this square root. I can use the fact that at large t, this goes to simply 1 over pi square root the minus b. Okay, so at the end of the day, this is like square root, this is b, so this gives you b power 5/2, and eventually you get minus t squared by just performing the integral 4 over 15 pi minus z to the power 5/2. Okay, so we found that there is a 5/2 exponent coming out here, and this is a bound, so it's telling you that phi minus has to be actually smaller or equal to 4 over 15 pi minus z to the 5/2. So this actually, for large negative z, rules out completely the cubic tail, okay? So it implies that the cubic tail cannot hold up to large negative values, so in the far left tail. It excludes z cube. And it turns out one can, so this is like the first cumulant, but of course I could try to calculate this expectation in a cumulant expansion. So I'm going to have second cumulant, third cumulant inside the exponential, and so on. And if I do that, this is what we did in this paper on the third line with Alexandre, and later on more systematically with Sylvain Prolac. We show that this is e to the minus 5/2, but if you have the next cumulant, so second cumulant, will give you z square, which is subdominant, and so on. So you can systematically look at the cumulants, and in fact we were able to sum up these cumulants and to find again the result of Mersenne, Sasarov, Mersenne, Prolac by this method of cumulants. I'm not going to describe it more in details here. Let me just point out again that okay, so the point is that for very negative h on the very left side of the left tail, we found that there is this 5/2 exponent. So it means that you can write it like this. And let me make the remark again that this can also be written as 4 over 15 pi h 5/2 divided by square root t. So again, you notice that this is the same form as a short time tail, and in fact the coefficient we will show later is the same. So it means that the tails on the far right and on the far left are established essentially immediately. What depends on time will be the intermediate behavior of the left tail between, so there will be a non-trivial crossover function now, phi minus of z between, for large negative z, we're going to have the 5/2, and for minus infinity, but we know that for z going to 0, it should be cubic. So in between there is a function, and I will now show you how one can obtain this function by so-called Coulomb gas method. And okay, so so until now I told you that there are two ways to calculate this function. One was this method of Palmvé, which was solved by Sasarov, Mersenne, and Prolac. The other one is via this cumulant method, which I started here on the board. We have done with Ivan, Gossal, and Tsai Coulomb gas method, which I will briefly describe. And a bit later, Lich and Tsai found another method using the stochastic Airy operator, which he managed to put on rigorous ground. So he actually proved that the function phi minus is the function I will show you. And a bit later with Alexandre, we actually showed that the four methods actually coincide completely. I mean, the saddle point of these methods can be mapped into each other. And we did it for actually a larger class of function of linear statistics. So KPZ corresponds to this particular choice of function phi, but you can do it for a larger class of function and study the linear statistics at the edge of a beta random matrix ensemble. So, okay, so let me now show you briefly the Coulomb gas calculation. So we have given what we have done now. Okay, let me write it here. Okay, so the function phi minus of z, we can rewrite it as the limit when t goes to infinity of 1 over t square times the log of the expectation of this product here, this sum of this a plus si, ai plus s plus function. And let me rewrite it directly, introducing the empirical measure for the Airy process. So I'm going to call it mu t. Okay, so the only thing I've done here is I've written that ai is minus t2 b I, and I introduced the empirical measure of this rescaled Airy process, and I put minus sign just to confuse you because, okay, that's how we did it in a paper. So we looked at the lower edge, if you want, but it's really a detail. So how do you estimate this? Well, you need a large deviation principle for the probability that this empirical measure equals mu, and it turns out that there is such a large deviation. Estimate, there is some functional of mu, and the way to get it is to use the Coulomb gas description in the bulk and then go to the edge. So I'm not going to make the detail, but this is what we did in this paper with Ivan, Corwin, Gosal, and Sai. So once you know this functional, you can immediately find phi minus of z to be the minimum of a whole measure of, okay, let me call sigma of mu, and sigma of mu is the integral dB mu of b plus this area of mu. And this measure is obtained by a limit from the bulk Coulomb gas, and essentially it reads something like this. It's itself some Coulomb gas. The only subtlety is that one has to subtract to the measure mu the Airy, what we call the Airy measure, which is simply actually here just the square root of just the semicircle, I mean the square root measure. Okay, so this is essentially a more or less standard Coulomb gas with some background subtracted. There's an additional term which I'm not going to write because it doesn't play any role. And this is obtained again from taking a limit from the bulk. So let me briefly describe the solution of the minimization. The solution of the minimization is, I'm not going to write any formula, let me just make a little plot. Well, I can maybe do it here. Okay, so it looks like this. Mu star of b so if the at equilibrium without the perturbations, like a perturbation, you have just a square root density, but then the Coulomb gas is pushed, and in fact the edge is moving from 0 to some u0, which depends on z. So it starts as a semicircle here. It has a divergent behavior near the point at which you perturbate, which is this minus z. So you can think of this perturbation of this Coulomb gas as some kind of soft potential, which looks like this. So this would be minus z minus b plus. So it's a soft potential pushing the Coulomb gas. And at this point, there is actually logarithmic singularity. And eventually, okay, my drawing is not very good, but eventually it joins the square root behavior a bit later. Okay, so this is what this perturbation is doing to the Coulomb gas. You can calculate the equilibrium measure, and then you calculate the sigma corresponding, and you find the following formula, which is this phi minus of z. So let me write it here. You will see it's quite simple formula. In fact, when I saw it for the first time from the Merson paper, it came out as some kind of miraculously simple. And I was convinced that one could get it from random matrix theory. Okay, so at least one can get it from Coulomb gas. Okay, so this is a function. And this function has all the correct behavior. It's cubic at small z. It's z5 at large z with some z-square correction and so on. Okay, so this is the calculation using the Coulomb gas, and let me make three remarks on it. First, we can extend this to KPZ in half space. There is a similar formula here for KPZ in half space with some specific boundary condition, where here actually you get here a power 1/2. And the power 1/2 actually drives you to the GOE instead of the GUE. And the calculation is extremely similar. It's a Coulomb gas with a different value of beta, and we get immediately that the phi minus for the half space is half of the phi minus of z for the full space. Okay, so this is first extension. Second question is about stationary or Brownian initial condition. So this is a conjecture. The conjecture is that phi minus z for the stationary or Brownian initial condition is the same as for the droplet. And this is again full space. Okay, I can get into the detail why we conjecture this, but this is what we believe. But we have no proof of this, or not even a complete calculation. But there are very good arguments. And then there is another one about the flat. And the conjecture here is a bit more shaky, but the conjecture is that there's actually a 1/2 factor. So, sorry, factor 2. So the flat would be actually twice the phi for the droplet. And the reason for the flat, I mean, this little argument I made about this area, the disorder in this area for the polymer to be smaller than average. So this would be for point to point, but if you do point to line, you see that the area is doubled, right? So of course not very good argument, but okay, it looks, huh?
Then the Brownian would not do it.
Okay, yes, Brownian is something else. You cannot really, okay. Yeah, I mean, it's not very good argument, just argument for physicists after a few glasses of wine, maybe. Okay, so let me finish with this short time, if I have time. How much more time I have? 7 minutes. Okay, so short time. 10 minutes. Wow, fantastic. So question on the large time? Okay, so short time now. So the short time we did in this paper, so the first paper we did the droplet initial condition with Majumdar and Sher, and the second one we did the Brownian initial condition with Alexandre and half space. And then we did later this expansion. So I'll just describe the lowest order expansion, but we actually managed to calculate corrections to this up to order T cube, I mean extremely high order, thanks to Sylvain amazing abilities, algebraic abilities, so it was really amazing. But anyway, we have a very good time expansion of this. But let me just discuss the lowest order large deviation. Okay, so the idea is to calculate again an expectation, and now I'm going to write it like this. Exponential of h. So I've just introduced okay, I've renamed things, and I've introduced a factor square root of t for some purpose. Here, h now is a bit shifted. There is some log in the shift compared to the definition I gave you before of h, but it's not very important. And then we're going to show that for positive z, this can be written as some function of z divided by square root t, for small t. And from this, just by simple Legendre transform, we're going to get phi of h to be the max over z of psi of z minus z exponential h. Turns out that this makes sense only for positive z. So we're going to have to extend this function psi of z outside of the positive axis to some interval, which I'll show you later. We managed to do that by analytical continuation, and then we get phi of h. So in just one nutshell, how does this psi of z looks like? Well, it's again a question of density. It's again this cumulant expansion. You can show that, again, the first cumulant gives you the correct result at short time, and then the higher cumulants give you higher order in time. And the first cumulant, you can just obtain it by some simple rescaling of A. And now we're going to have the log of the Fermi factor in its full glory. So it's this function times some density. And again, this density for the droplet initial condition is again square root of A. Okay, so that will give some polylog function. And there is also an expression for this density for this Brownian initial condition. It's not the Airy kernel anymore, it's a deformed Airy kernel. It's more complicated, but there's a formula for this density in terms of Lambert function. So at the end of the day, let me write the result for the droplet. So as I said, it's a polylog function, and it can be written like this. So I'm going to rewrite it just to show that there is some structure actually which we don't necessarily understand, but okay. And now the stationary one, so the Brownian one, is the same formula here, except that it's Le2 of minus z over p squared. Okay. And in fact, we also did the half space, and the half space has also a formula like this. So we don't know why they are so closely, they look kind of very similar, but because the calculation is really not so straightforward, so we don't know why, but this is what seemed to happen. Okay, so let me now briefly tell you. So this function psi of z, we have to, so it's defined originally on the positive axis, which correspond to the interval of h, which is on the right, on the left side, negative h. So this is the side which is easy to calculate at short time. At large time, we saw that this is the side which is the most difficult. At short time, it's the most easy. What is difficult at short time is to get to the other side, to the right side, because there is a branching point here, so one has to do some analytic continuation. And for the droplet, it's not too difficult, so we obtain this formula. And this branch point is actually kind of fictitious in some sense, because it's, the function of h is completely analytic around this point. And we get these two expressions, but it's completely analytic, and we get the tails. So again, I didn't explain it again, but the tails on at short time on the left is exactly what we found at large time on the outer tail, and on the right tail it's exactly the same also. And this happens not just for the droplet, but happens for all initial conditions we have managed to look at.
I don't understand the connection to the exact formula there, which looks a lot.
So this is large time. This is large time. This is short time. But it's the same tail. So the left tail at short time is the outer part of the left tail at large time. Exactly the same. Okay, so this is again, I'm doing now short time. So we also looked at the Brownian initial condition, and then there is something very interesting which happens, is that there is actually a phase transition. So there's a third point in this branching, in this space here. There's a third point where there's actually a true transition, and there are actually two branches here. This is a derivative of phi. And the stationary initial condition, the Brownian initial condition, corresponds to this branch, which has this breakpoint here. And amazingly, the analytic branch corresponds to the flat initial condition. So this was actually shown, I mean, there's a symmetry between the two, which was shown by Merson and collaborators. And they didn't have really the formula, but they managed to do the symmetry. So we can conclude that this actually, up to rescaling, is a flat initial condition result. Okay, and so there are some complicated formula for the Brownian case and for the flat case because of this more complicated structure, but I won't get into it. So let me just finish by showing some numerical simulations. So Alexander Hartmann is a great specialist of doing this importance sampling kind of techniques where you can actually go to events which have probability which are astronomically small, like 10 to the minus 100, so you will never see them in the experiment, at least naively, but you can see it in the numerics. And this is done by doing Monte Carlo at the same time on the disorder configuration and on the polymer. It's done on the polymer at high temperature on the square lattice. And as you can see, the fit with the prediction is quite good for short time. These are the detailed plot. This is a prediction and these are the data. This is the 5-half side and this is the 3-half side. And then he pushed it to larger time, which requires much longer polymer because you have to scale with the temperature and so on. And okay, it's not so good actually, and that is still quite good, but it's not. Okay, I mean, the way it's plotted, you cannot really see the function phi very well, but let's say it's acceptable, but it's not a very stringent test on the function written on the blackboard. Okay, so just to finish, let me just say that we are, okay, so these are a set of results, but we are far from a full space-time understanding of the large deviations. For instance, for 2 point, there are no exact solution at finite time, so maybe one can do some clever guess on, because, I mean, information we need from finite time is not the full information, it's only this limit, but still, it's not known what this limit would be for 2 point, for instance. So it's an open problem. It would be nice to be able to bypass this exact solution in some way, but another interesting question. Okay, so this optimal fluctuation theory approach of Korshunov and Merson amounts to find an optimal configuration H of xt and an optimal disorder configuration, so that to optimize the height, the probability of the height at some point 0. So that's, you get some coupled equation for that. Saddle point equation is valid only at small time. You can control it only at small time. But there are some nonlinear differential equation, and we know on the other hand that we have this exact solution. It would be nice to understand, if these things, how these things can fit together, because up to now they have been able to solve this equation only in some limits, in far tails. But maybe there's some more integrability behind this, I don't know. And then there is a question of universality. Of course, these functions are not supposed to be universal, but still one can ask what happens if one changes this nonlinear term in the KPZ equation. For instance, is the coincidence between the short time tail and the long time tail still hold in that case or not, and so on. Okay.
So regarding the short time dynamics, so you have this saddle point,
yes.
And then there should be some optimal
Yes.
way to go from your initial data to whatever H you required.
Yes. Mm-hmm.
And do you, I don't know if you have access to how this evolves, but can you see some special guess on how it happens, which is maybe...
Yeah, I mean, there is some exact solution of these equations, when H is very large, either on one side or the other side. And okay, so I haven't looked into I've looked on one side, but the other side it was done really by Merson, and I think he and Korshunov, and they have, this has some kind of exact solution in both limits. But for arbitrary h is not known.
Okay, but the idea usually is in other cases,
Yes.
people make the additivity principle approach where there is some special guess on how this optimization problem is going to be solved. And this is works in many cases. So
Okay.
I'm wondering if there is some clever guess here that could actually work for.
Well, that would be fantastic. I mean, you should look at Merson's paper and maybe, if you have any guess, more than what they've done. I mean, they've done already some nice work, but it would be nice to have something more global than what they did.
If there are no more questions, then let's thank our speaker again.